Hello everyone. Today we'll be talking about the heap data structure as an example of instance-based simplification in the context of transform and concur. So, before starting the discussions about the heap, I would like to remind you how you can represent a binary tree. Okay, so remember that if I have a binary tree, okay, what I could do is I can represent this with an array. How I do it, so if this is my binary tree, so root is 0, 1, 2, 3, 4, here it is 5. Although there is nothing for the position 6, I will use 6, and then 7, 8, 9, and 10. These are all empty, right? And then 11 and 12, right? So if I have an array starting from 0 to 12, okay, so 0, 1, 2, these are all occupied. What is empty? 6, position 6, it is empty, right? And positions 8, 9, 7, 8, 9, and 10, these are all vacant positions, but they are here. So let's say these are empty, okay, and then you have it. The moral of the story is actually when you have an array, actually this array encodes a binary tree. Okay, so that is something good to remember because we said that we will be talking about an instance-based simplification. That means I have a problem to solve, and while solving this problem, I would like to transform the instance. So that transformation is just a simplification. So that means whatever the input is, I would like to reorganize this input, make it simpler for the problem that I will try to solve. So when we talk about the heaps, actually the problems we are focusing on necessitates fetching the minimum or the maximum element from a set. These are the problems such that you will be always dealing to find the minimum or maximum or S of a set. So that is why whenever you have a problem that you will need frequent access to the minimum or the maximum of a dynamic set, so we should all remember the heap data structure. Heap is also known for the priority queues. So priority queues means, okay, so we are waiting for a service and each one of us has a priority. Whenever someone will be granted the service, so they check the priorities and the highest priority is given that service. So that doesn't mean that the order that we have been waiting for the service does not determine our priority. Someone may come later, but since he or she has a higher priority, they can get the service earlier than the previous arrivals. Okay, so that's the priority queue. So remember the banks. Okay, so when you go to a bank, so you get a number from the queuematic, and that queuematic, so there might be some cases that someone coming after you, so may get the service earlier because they have a higher priority. Or in an emergency service in a hospital, so everyone is waiting, but whenever someone arrives with some very, very urgent emergent care, then they will be given the priority and taking the service first, right? So in all of these scenarios, what do we need? We need to find the minimum or maximum of a set. So that is why the heap data structure is very useful. So let's see, what is a heap? A heap is a binary tree. Okay, so that is a binary tree such that except the leaf level, it is a complete binary tree. Okay, and all the leaf nodes are on the same level. For instance, you see, so this one is a complete binary tree. right? And this is the leaf level, okay? So what we say is I will have a complete binary tree here, and then I will have some leaf nodes. So this is called a heap with the shape property. So it will be like that. So the important point is all the leaves should appear towards the left side. Okay. So there cannot be a gap between the leaf nodes. For instance, if I get this out and make this like that, so this is not a heap because there is a gap on the leaf level. So on the leaf level, no gaps are allowed. You see what this brings. So let me draw it again. So this is my complete binary tree, right? So since that is a complete binary tree, I will have an array from 0 to the n minus 1 to the n minus 1, right? And every position in this array, they are all occupied. So they are in this complete binary tree. And then I have the leaf nodes. Since the leaf nodes are ordered from left to right without any vacancy, so that means I will have the leaf nodes here and there will be no empty positions. Moral of the story, so when you have a heap, this is no other than an array. Okay, so this is just an array. And it confirms the shape property. Let's remember again. So all the leaves are at the same level, and all the levels except the leaf level, it is a complete binary tree. Okay, so this is a heap. So this is the shape property. What else I have? I have the second property, and we call this actually the heap property. It depends. So let's assume I'm creating a max heap. If I'm creating a max heap, every node is greater than all the others, all its descendants. So 10 is greater than 5 and 7, right? And 5 is greater than 4 and 2, and 7 is greater than 1. Since all the nodes confirm the heap property, so we call this a heap. In that sense, what we are sure is if this is a max heap such that every node is greater than its children, then the maximum value is always at the root. Okay, so if it is a mean heap, then what will happen? Every node will be less than their children, and that will dictate that the minimum value should be at the root node. That is why if you just when you just represent this heap with an array, you are sure that the minimum or maximum, according to your heap construction, is always at position 0. That is something very useful. Why? Because if my problem needs to access the maximum or minimum frequently, then it's very easy if I represent the set with an array and keep it with the heap data structure, then whatever I'm looking for is always available at position 0. Okay, but in this heap structure, there might be some new additions, there might be some deletions, and these should not destruct the heap property. Okay, so there should be good ways of achieving these insertions and deletions. So this is the first step, how you can insert an element to a heap. It is very easy. First, I would like to show you on the array. So this is the array, and this is the array you maintain as a heap. So these are the current elements. Whenever you would like to insert something, you just insert it, append it as the last element of the array. Okay. In other words, if this is your current heap data structure, whatever you will be inserting, you will be just making it the next leaf node. Okay. Uh, One question that may come to your mind is, what if the leaf level is all occupied? So then no problem. So you will start from the first element on the new level, okay? And this will not be problematic for the shape property because now it is a complete binary tree also. But let's see how we can add 10 to this already maintained heap data structure. You make it as the leaf node, rightmost leaf node at the leaf level. You make it 10. But what we need is, we know that, so this is a max heap, right? This is a max heap. You see 9 is greater than 6 and 8. 6 is greater than 2 and 5. And 8 is greater than 7. But when you insert 10, 8 is not greater than 10. So that means after making this insertion, I should change their position. So 10 will come here and 8 will come here. Since you have updated this node, you have to check its relationship with its parent. So this is 9, this is 10, and its parent is 9. So that means this guy should go one step further and become the new root. This is the resulting heap. Okay, good. This is my new heap, and I know that whenever I insert an element, there might be a movement of this element from the leaf node towards the root. So that is actually called up heap bubbling. So this is like a bubble. So it's going up, up in the heap, and up until the root node if necessary. Okay. So let's make another insertion to this tree. So let's say I would like to insert let's say I would like to insert 4. Okay. So whenever I would like to insert 4, so this is already occupied. So 4 will come here, right? 4. And then I will start checking the values. 4 and 2. 4 is greater. So that means 2 will come here and 4 will move here. And that is 4. I need to check its parent. It is 6. Now I stop because I know that 4 is less than 6. So this is my new heap after inserting the value of 4. Okay, so that is the heap insertion. One more question. What would be the time complexity? So that's actually almost trivial now, because if you have n elements, right? So you know that the height of this tree will be around log n or log n plus 1. So that means whenever you insert an element, the maximum amount of movements that will be subject in your up heap bubbling is equal to log n. So that is why insertion is log n time. Okay, good. What else? So similar to insertion, so there might be some deletions. So at deletion actually should be considered in two ways. The first one is I would like to remove the root. Why? Because in my problem, I may need to fetch, I may need to extract the minimum or maximum value according to the heap structure. So since we'll be talking about always the max heaps, so I don't want to repeat this again and again. So when we say heap, so let's assume it's max heap unless we mean the otherwise. Okay. Okay, so this is a max heap and I would like to remove the root node. So root is 9. Okay, so for the removal, what I do is first I swap it with the last element in the leaf. In terms of the array representation, what happens is if you would like to remove 0, what you do is you get this out and actually move this element, the last element, to the root position. Surely, when you move the last element to the root position, the heap property will not hold. And then you need to check. You need to check this new root with the children. Okay. So this is 1. There is 8 and 6 here. So that means 8 should move to here and 1 will come here. Okay, so now we are going downwards. So when that is 1, you compare 1 with 2 and 5, and you see that, okay, so 5 is greater, so that means 5 will come here and 1 will come here. And at the end, you will be having this new heap. Now you see that actually it is good that so 8 is here as the maximum element, and we have the other elements confirming the shape and heap property of this data structure. But I always like to remind you that so you are only doing operations on an array, okay? And this array, making those operations are easy with this structure. Okay. Why they are easy? Because this is a binary array, and I know that who are the children of any node. So 2 times this node will come here, and 2 times this index plus 1 will point here. So these will be the children of this guy. So that is why everything is easy here. Okay. So that's the removal. And if you would like to remove any element, you don't want to remove the root element, but you would like to remove or change the value of something in between. So that's again not that much difficult. So let's assume you would like to change the value of, let's say, this. First, let me do the removal. Okay, so now I would like to remove. So let's do it. So if you would like to remove 8. Okay, so what you can do is you can move 8 to the last position and you will make this 1, 1. So you will get this out. Now you have 1 here and you have to check both the parent and the children. So that is a max heap, right? So when you check the parent, you see that 9 is greater than 1, so you don't need to do any upward movement. But when you check 1 with 2 and 5, you see that 1 is less than these guys. So what will happen? 1 will be swapped with the largest of those elements, so 5 will come here. So at the end, you will have 9, 5, 2, 1, and 6 here. So now you have removed an inner node. Similarly, you can change the values. So let's assume I decided to make this value not 5, but 13. Okay, so if that is 13, then I will make the up heap bubbling to see the correct position. So what will happen is 8 will come here and 13 will come here and 9 should be here, right? So again, removing any element, removing the root node or inserting a root node, inserting an element, sorry. So these are all logarithmic time operations with the heap data structure, which is very nice. Okay. So now this question is very important because at the beginning we said that heap is an example of instance-based simplification in a problem. Okay. So to make it visualizable and simple, so let's assume I give you a set, okay, and I want you to find the minimum element, okay. So since this is a set, I give this as an array. You decide that since I will be fetching the minimum, okay, so let me reorganize this array as a heap and let me construct this heap. And how you can do this? So that is extremely important because if constructing the heap is more expensive than doing the job itself, then it will make much sense. Okay, so now we focus on how I can construct a heap given an array. Okay, the first way is what I can do is I can just take the first element, insert it into an empty heap, and then take the second element, do the insertion. Okay, and then take the third element, make the insertion. Okay, so that is something like creating a second array one by one by copying the elements and doing the necessary operations. The not so good part in this construction is that after some time, so whenever you insert a new element, you may need to have some up heap bubblings, and that may cost you log n. Since you will be making n insertions, so in the worst case, that will be an n log n time operation. That means from a given array, I can create a heap in n log n time. Trivial, that's a top-down construction. I will insert every element one by one. But if I do it with an n log n time, and going back to our previous discussion, I'm just trying to find the minimum element, and I can find the minimum element in linear time, right? And then why do I bother to create a heap with n log n time, which is worse than the naive approach, okay? This is a fundamental question that comes to the table when you deal with heaps, and the heap is a very powerful data structure because you can construct heap in linear time. So we call this the bottom-up construction. And that brings us a lot of gain in many problems that we will see some examples in the class, okay? Okay, so now we have seen that I can have the top-down construction. It is n log n time, trivial. But now I will show you how you can construct a heap in the bottom-up fashion, and this will have a better efficiency of O(n) time. The first observation that we will do is, so this is my heap. This is my array, sorry. So input array, okay? And let's say up to that point, I have the complete binary tree. So if that's a zero-based index, that starts from 0 and comes to some 2 to the k minus 1 position. And then I have something here. So 2 to the k is a lot later. Okay, so that means all these elements here are my leaf nodes. Okay, so once I have those leaf nodes, what I will do is I will not touch them initially. Okay, I will keep them as is, but I will find their parents here. So because they have their parents occupying the positions here, right? And then I will check whether I need to make swap between the parent and its children one by one. Once I do this, okay, now I am done with this part, and I will check the parents of these parents. Okay, so now the grandparents. But the issue is, the point is, actually it will be always getting smaller and smaller, and I will be making a linear move from left to right. Okay, so this is the high level sketch. Now let me show you how you do it on an example. Here we use one-based indexing, right? And we have 15 elements here, okay? So this is a complete binary tree, and that means the ones after position 8, right? So these guys, okay? So these are my leaf nodes. So first, assume hypothetically you have placed all your leaf nodes. Okay, so and then I will check their parents. Who are their parents? Their parents are here. Okay. 25 at position 4 is the parent of the elements at position 8 and 9. Why? Because 2 times 4 is equal to 8. 2 times 4 plus 1 is equal to 9. And that means 25 is the parent of 16 and 15. Okay. And now I'm creating a mean heap. Okay, so that means the parent should be less than their children. If that is the case, I see that, okay, so 25 is not the minimum element. So the minimum element here is 15. So what should happen? 15 should come here and 25 should come here. So 25 will go there and then 15 will be replaced by this one. Now you are done with this section and you go for the next one. Okay. For position 5, Who are the children of position 5? They are at position 10 and 11. And I check 9 with 4 and 12. So trivially, so 4 should be moving that position. So that means these two guys should swap. Okay. And then you do the same thing for 6. The children are 12 and 13. So that is 6, that is 7, and that is 11. So that means 6 should be moving to that position, right? And the last one is position 7. Its children are here. And actually it is fine because 17 is less than 23 and 20. So at the end of those verifications, now you are done with the last 2 levels of your heap. Up until now, everything is under control and you have this structure, okay? In other words, you have converted this input array to this one. Okay, now I will focus on the parent of the newly established nodes. Okay, so I have just touched these nodes and now I will check which ones I need to check these guys. So this will happen on the next slide, I guess. Okay, I see there. Okay, now we come here. So that is 5 and that is 8. Okay, at position 2 and 3. Okay. You first place 5 here. So 5 is here. And who are the children of 5? 2 times 2 is equal to 4. And 2 times 2 plus 1 is equal to 5. 15 and 4. Okay, so 15 and 4. Since this is a min heap, what I should do is I should move 4 to that position and 5 to that position. So that means, okay, now it is 4 and it is 5. Since that is 5, since I have updated this one, I should check its children. Who are the children of position 5? So it is 10 and 11. So they have the 9 and 12 values. And 5 is less than these guys. So it is fine. So you are done. And now for the next one, position 3. So let me make a clearing. Okay, so now I'm focusing on this one. So that is 8. And who are the children? It is, they are 6 and 7. So you have the values 6 and 17 here. And if you make the verification, so you see that, okay, I should make a move because 6 is less than 8. And since this is a min heap, what should happen is I should copy 6 here and 8 here. Since you have updated this guy, you have to check its children. Who are the children? 6 times 2, it is 12. 6 times 2 plus 1, it is 13, right? So 11 and 7. And 6 is less than these guys. So you say that, okay, I'm fine. Okay. Okay. Oh, sorry. So we were here, right? So 6 has gone to that position. So that's the second place. So I have 8 here. So yeah, since that is 8 and that is 7, this should be 7 and this should be 6. This should be 8, sorry. And you will be having this heap structure at the end. Now, what you have done is you are sure that the last 3 levels are all okay. And the last one is I will need to check the root. And we will do it on the next slide. Okay, now I'm checking the root. That is 14. And who are the children of 14? So it is 4 and 6, right? So these are the children of the first node. And when we make the comparison, we see that, oh yeah, so 4 is less than 14 and also 6. So that means 14 will come here and 4 will come here. Okay. So now I have 4 here and 14 here. Since I have updated this guy, I need to check. So that is 14. 14 is less than 15. It's good, but 14 is not less than 5. So that means I should make this 14 and this should become 5. Okay. So once that is 14, again, I will check the children. So they are 9 and 12. So there's one more step. 9 should come here and 14 should come here. You see, while placing the root, correctly placing the root, you made a traversal of 3 levels, right? And what is the complexity of this construction and why this is linear? I would like to take your attention to a point. Okay, so you do not make any swaps on the leaf level at the beginning, right? So you don't do anything at the beginning. But when you check just one before the leaf level, okay, so what you need is you may need to have a single swap because you have only one leaf level to consider. So there can be only one swap. Okay, so when you go to the next level, any item at the next level may be subject to 2 swaps. Okay, any item on the one upper level, they may be subject to 3 swaps. You see? Okay, so if you just formalize it, actually, if you are verifying the root node, that may be subject to some age swaps. Age is the height of my tree, okay? And then for the children of the root, so there are 2 of them, so there's only one root, and there are 2 children of the root, okay? And they may be subject to h-1 swaps. And now on the next level, I have 4 nodes, each of which may be subject to h-2 swaps, okay? And this gives me a very nice closed formula. Okay, so the total number of moves for I is equal to 0 and h is equal to actually log n. Okay, if you make this summation I times 2 to the I from the series, from the algebra, we know that this is less than n. Okay, so that is why even in the worst case, the total number of swaps cannot exceed this value, okay? And at each level, we also consider that we have at most 2 comparisons because whenever you are updating an element, first you have to check the children, okay? So find their, if this is a min heap, so find their minimum and then compare this minimum with the new value. And so that makes a 2 comparison at most at each level. So 2 times n, so it is always less than 2n. So we say that the construction time, so the bottom-up construction time of the heap is a linear operation. We call this the bottom-up construction because you start with the leaf nodes and then you check the level just before the leaf nodes and you go towards the root. And notice that at each level, you will be doing half of the work, you will be verifying half of the nodes when compared to the next level. Okay, so that is the heap construction, and we know that you can just construct heap in linear time. So I think this is my last slide. So once you can construct a heap in linear time, how about this? Whenever someone provides me some number of items to sort, what I will do is I will first reorganize this input as a heap. So that is an instance-based simplification. You give me an array, I take this array, and I construct a heap. And I can do it in linear time. This is not changing your instance. I am just changing the organization of your instance and making this array a heap. Okay, so after this construction, you asked me to sort it, right? And let's assume I make my heap as a min heap. What I will do is I will fetch the root, take the minimum, okay? And this will be in log n time, and I will do it n times. So this will have a total cost of less than n log n. So heap sort becomes an optimal time sorting algorithm with n log n timing, okay? So let's do it first. This is the given array 2, 9, 7, 6, 5, and 8. And first I construct the heap. Okay, so this heap construction, so this is 1, 2, 3, 4, 5, 6 elements, right? 1, 2, 3, 4, 5, 6 elements. Okay, so initially, so that is 2, that is 9, and that is 7, that is 6, that is 5, and that is 8. Okay, and what I will do is these guys, so these are my leaf nodes. I will not touch them, but first I will start with these ones. So you start with 7 and you check it with 8. So, and you do the necessary updates. And so I think here they are creating, yes, they are creating a max heap. Okay. So 7 and 8. So 7 comes here, 8 comes here. So 8 comes here and 7 comes here. And you can keep doing the same operations, and at the end you will reach this structure. Okay, so let me draw it. 9, okay, 6 and 8, and I have 2 here, I have 5 here, and I have 7 here. So, and I can do it in linear time. Okay, so this is linear time. Now, what I will do is I will fetch the maximum. I know that the maximum is at position 9, so I get it out. And once I get this out, I should move first 7 to here. 9 is out. So 7, 6, and 8, what should happen? So 7 will come here and 8 will come here. Okay, and now this is my new heap. And what I will do, I will go and fetch the root. Now it is 8, okay? And then you will keep doing that. So at the end, you will have 9, 7, 8, whatever, these sorted elements, okay? So that's called the heap sort. And summarizing what we studied, okay, so heap, my suggestion is to think heap as an input array. So you are given an array, and an array defines a binary tree, right? And on this binary tree, by reorganizing the elements in this array, you turn it into a heap. Still, you have an array, you just change the positions of some of those elements. And with this construction, you are sure that if you are constructing a min heap, the minimum value is at the initial position. If you are creating a max heap, the maximum value is at the initial position. That means whenever you need the minimum or maximum, you can do it very efficiently in constant time. You can go and fetch it. But after you fetch this element, you need to make some reorganization in your data structure to keep the heap property, and that will cost you log n, which is not bad. Okay, so that means after each operation, I will do a log n time housekeeping on my array to sustain this heap. Okay, and with this way, actually, you may be answering many of the questions that includes minimum and maximum access very frequently, very efficiently. Okay, and yeah. Okay, so that is the end of our heap discussion, and I plan to cover some example problems by using the heap in the class. But for those of you who would like to make a preparation or do something more, what I suggest is you may be working on the Huffman coding, okay? Huffman coding, and it is a very good implementation. It's a very good understanding of why heaps are very useful. We will be discussing this later. Okay. Thank you so much and take care.